Hopefully you can all see that okay. Jerry, have you started the recording?
Yeah.
Okay, perfect. Cool. Yep, all right. So my name's Richard. I sort of head up the electronics and partially software side of things on the rescue robot project that I'm sure you've all seen sort of in your time in the society. I'm sort of one of the main people doing PCB design in the society, but that by no means makes me an expert, to be honest, but needs must. So if you guys could, it'd be good if you could turn on your cameras. Like, it'd be good to have some sort of interaction back and forth, but I understand what sort of Zoom lectures all day are like, so don't worry if not. And so feel free to ask questions as we go through. Put your hand up or send a message in the chat and so on. And we will get started, I think. So I guess the first question is sort of why make a PCB? A lot of people build sort of mini robots on breadboards and things, so on. But I'm sure you've sort of all encountered the horrors of building things on the breadboard, debugging for hours on end because it ends up you have a little broken wire or your breadboard's not quite right. So that's sort of essentially the reason, well, a big part of the reason anyway, we make PCBs. So you can go from sort of a simple idea you have in your head or a breadboard like this. You can fully characterize it in a schematic built on a computer, which sort of defines every single detail of your circuit. And then you can design and get manufactured a PCB where you can solder all the components onto it and everything just sort of works. You don't have to worry about dodgy connections and things or wires coming out of breadboards and so on. And it just makes things so much cleaner, because then all you need to have coming off this breadboard in terms of wires is, say, some wires to a power supply, like some AA batteries or something, wires to your motors, and wires to your sensors, say. So how does a PCB sort of work? It's quite a good thing to have an idea of to begin with. So if you look on this here, you can see there's sort of two different colors of material on this PCB. There's a sort of dark green and a lighter green. And these light green bits are where there are tracks, which are just sort of where this bit of copper still exists. And anywhere where you don't want a track, essentially it gets etched or drilled off and the copper is removed. So that you end up with essentially these long wires across the surface of the PCB going in between components. The sort of PCBs you'll be working with will be 2-layer. So you have a copper layer on the top and a copper layer on the bottom. And essentially this is so that if you have two tracks that want to sort of go across each other, you can run one on the top board and one on the bottom. And you can then swap between layers using something we'll talk about later called vias, and that helps to be able to make much more complicated PCBs. So when it comes to sort of component mounting on PCBs, there's sort of two different types of components you'll come across, basically. There's through-hole components, and I was trying to get a section, sort of side view of this, but essentially these leads go all the way through the board and come out the other side. So there's holes all the way through the board, and you solder them on the other side of the board, and that makes contact all the way through. Or there's surface mount components, and these are usually used when you want to make like much smaller PCBs, so you want to miniaturize your stuff. And these just sit entirely on the surface of the PCB. And as you can see here, there's sort of a track coming out this side, a track coming out this side. And there's nothing going through the whole board. So you can actually do sort of double-sided boards as well. So as these are just surface mount, you can have the same thing also on the other side, doing some other stuff as well. But I think for you guys, the focus will be largely on through-hole devices. So on the right here, there's also an example of, again, sort of a through-hole versus surface mount device. These are ICs or integrated circuits. So these can be anything from, just sort of sets of simple logic gates, like NOT gates, AND gates, and so on, all the way up to, if any of you have an Arduino handy or an Arduino Uno, say, you should see a chip that looks a lot like this sat in a slot on your Arduino Uno. And that's like a full microprocessor in one of these little packages. And as you can see, normally these legs on the through hole can go all the way through the board, or more often they slot into a slot which is again another through-hole component that you solder on the board, and then you slot that in. You slot this IC into the slot, and that means you can sort of interchange ICs if one of them dies or so on. Whereas with this through-hole surface mount one, this will be soldered directly onto the board. Yeah, so I said I'd talk a little bit about vias. So this is sort of how you swap between a copper trace on the top layer and the bottom layer. Later on, we'll go on to how to make these in KeyCAD when we're designing our PCB. But this is the essential idea. Vias and these sort of through-hole holes that I showed for putting in the different through-hole components are very similar. A via is just a very small hole, basically, which has copper plated all the way through, so you can connect, from one track on top here to one track on the bottom. Some useful things to know. You don't need to remember all this. I can send the slide and so on. But there's sort of a very confusing unit that is used in PCB design electronics, and it's sort of the standard, unfortunately. And it's the mil, which is not a millimeter. It is 1,000th of an inch. So 2.54 millimeters. So a lot of components have their pin pitch designed in sort of a round number of mils. So these sort of pin headers that you see on a lot of devices, like for example, if you have a little Arduino, again, you'll see these pin headers soldered on the side of it. These will almost always be spaced 100 mil apart, or 2.54 millimeters. So that's useful to know for if you're designing to interact with other devices. Here's what I talked about earlier. So the socket for these through-hole ICs to sit in. So again, yeah, basically this is the bit that actually gets soldered onto the board, and then you can slot the IC in and out, which is quite useful because if you accidentally short an IC or something like that and break it, you can just replace it. It's quite handy. But yeah, again, these have the same sort of spacing as these pin headers. It's all imperial, using these 100 mil increments between each pin. Finally, the surface mount ICs, which you probably won't get into, but useful to know anyway. These are like a lot newer technology. So they actually, thankfully, use metric, which means these are often going to be like, I don't know, say 1 millimeter or 5 millimeters apart, basically, which is nice because it's metric. But then say you have through-hole components like these interacting with metric components, you can see usually you design all of these parts on a grid. And for this, you might design them on a 100 mil grid. But obviously a nice metric component is not going to fit on something that's based on an imperial grid. So that's something you need to worry about if you're trying to mix the two. Yeah, so soon we're going to move on to sort of a quick demo in KeyCAD of building a PCB. But something else you have to keep in mind when you're designing a PCB is the manufacturer's restrictions on what they can manufacture, basically. So this is all going to be down to the process in which they design a PCB. So, sorry, which they manufacture it. So earlier on, I showed you that sort of 5-layer board, whatever it was, which has like solder mask and then the copper and then the substrate, which is just like a bit of fiberglass that everything sits on, and the same thing on the other side. And essentially, there's a few different ways you can etch out those lines in the copper to get rid of them, to build your tracks. So sort of the oldest and the most common way, I guess, at least before, was the sort of wet etching process. So basically it's a chemical etchant. They sort of print out the design on the PCB with something that's going to block any sort of acids or something. And then they dip it in like an acid, and that etches out the parts of the copper that you don't want, and you're left with only the copper you do want. This is usually a bit less accurate, and you can have some problems with it, but yeah, that's sort of the first process. You can see the EDG in this case is the electronics development group in the engineering department, and they provide sort of free PCB manufacture for societies, fourth-year projects, and so on. So these are their manufacturing restrictions. So you can see here we have tracks and gaps down to 12 mils, which means you have to have a track width of at least 0.3 millimeters, preferably more, as they say here, at least sort of 0.4. And the gaps between those tracks also have to be above those sizes. If you're using if they decide to use the routing machine, which I think is sort of, if you have a very specific need for it, you can actually get tracks and gaps down to 0.2 mil. But when designing your PCBs, I'd say stick to these first set of restrictions. These other restrictions, minimum drill size, I don't think you need to worry about too much. Maximum sheet size, again, don't go bigger than 26 by 20 centimeters, but I don't think anyone will be designing one that big anyway. And yeah, down here is the sort of definition of the mill or the file. Yeah, so this is some examples of PCBs within the rescue project. Thought I'd just give you a quick sort of example of what we've done with these now. So these are quite busy PCBs. These are all within the rescue project. This is sort of the main PCB on the left here for the robot. So this provides a couple of different bits of functionality. It provides power monitoring. So you can see these two devices here. These are actually measuring the current going in and out of the robot, which is a good thing to keep track of, because then you can see sort of your power consumption. If there's a very high current, you probably want to cut off the power supply. So that's what these are called relays. I'm sure some of you have come across them before, but they're basically like an electronically controlled switch. So if we detect the current is getting too high through the robot, we can cut off all the power temporarily and sort of check out what's going wrong. And yeah, and it provides a few other things, like there's a battery attached that monitors the battery level. And as well as this, there's also a connector on here. It's probably quite hard to see on your screen, but down here there's like a sort of 10-pin connector that goes to this touchscreen shown in the middle, and it does all the control for that. And this is all done, all that control is done using this microcontroller here. It's very similar to an Arduino. You program it using an Arduino IDE. It's called a Teensy, but yeah, it's just a little bit faster than standard Arduino and has a few more pins. Also in this sort of one PCB we didn't design. This is a DC to DC converter. So that's used for swapping between sort of DC levels, DC voltage levels. So if you have a battery that outputs 24 volts, for example, and you have some motors that want 12, this will do the conversion between those voltages. And as these big beefy heat sinks, because this is actually for the motors on the robot. And yeah, it has a lot of current going through it because of that. Yeah, so here you can sort of see, it's not the cleanest thing in the world, but without these PCBs, this basically would be infeasible to create. So that sort of shows you why we create PCBs. And yeah, here on the right is just some examples. We're sort of building a version 2 of this PCB. So, we want to integrate, you can see on the right here, there's actually another PCB as well as the main PCB, as well as this DC to DC converter, this little random board here, and so on. So we're trying to integrate that all into one with some nice new components as well. So we've designed some prototype PCBs of that. Yep, so at the end of the slide is just some useful links to different things. So the first link here takes you to the Dyson Center website here. Oh, with my Chrome unfreezes. Yeah, there we go, sorry about that. Yeah, so this takes you to the PCB production part of the Dyson Center website. So there's a lot of useful information on here about sort of what they will produce, the requirements I was talking about before, shown down here, and yeah, everything you should need to know, as well as like the link to KeyCAD downloads. There's also a 20-minute KeyCAD guide as well that probably will be quite a bit better than my one, but I'll still run you through it anyway. And yeah, other than that, there's like another couple of links. So in KeyCAD is quite useful. There's a lot of buttons, so remembering the keyboard shortcuts is quite a useful idea, but we'll go through that later. And as well as this, there's the Robotic Society wiki page on sort of where to source components from. There's a bit of a process depending on how exactly we get the money for the components you're buying. So there's some suppliers we have to go through if we're using one type of money, and if not, there's like some suggestions for where else to get your components from. But yeah, if it's sort of money you're free to use, honestly, like eBay, Amazon, good places to get components from. So yeah, so I guess now I will go on to a quick sort of KeyCAD tutorial. I won't go through the install, that's all on the website. I'm going to go from, presuming you've got KeyCAD installed. So once you open KeyCAD, you'll either be you'll be presented with a screen like this. If you've worked on a project before, obviously that will come up here, but we'll presume you haven't. So create a new project. You can just go File, New, Project, like any other piece of software, basically. And then, save it somewhere sensible. So I'm going to call this PCB Demo Project. Hit Enter, and you'll be presented with two files on the left here, basically. So the first of which is the schematic file, which is where you're going to set out what components you're going to use and how they're going to be connected. And then the next is the PCB file, which defines the PCB layout and so on. So obviously you want to start with the schematic file. So if you double click on that, it'll bring up a schema or something. I don't know what it's called, to be honest, but this is where we're going to set out the PCB, the sort of schematic for the PCB. So I'm going to do a very basic PCB here, just for the sake of time. I'm just going to have an Arduino that's going to be powered by some external power source, a couple of potentiometers connected to it, and a couple of LEDs. So yeah, we'll just sort of get started with that. So the first thing you probably want to do, KeyCAD can have a bit of a funky zooming convention. You'll know what I mean if you start using it and things feel weird when you're trying to zoom in and out. It's this setting here. If you go to Preferences, Center and Warp Cursor on Zoom, untick that, and it will be sort of a more normal zoom in thing. You'll understand when you try and use KeyCAD. But yeah, so the first thing we'll do is, so we want an Arduino Nano. So it's usually best to start off with your biggest component that's going to have the most connections in. So yeah, so here we chose this little add symbol button on the right, and then you have a whole library of built-in components that KeyCAD comes with, and this is going to cover a lot of the components you need. If you find something that you want to add that isn't in here, you're going to have to follow a bit of a process, but I will send a link for that. I'm not going to go through that in this tutorial. So yeah, up in the search box at the top, we can just type Arduino, and you can see here Arduino Nano V2, and that's what we want. So you can just press OK and insert it into your schematic. So now you have the Arduino Nano schematic, and the first thing we probably want to do is add some power supply. So you can see here we've got V in and ground, and they're currently not connected to anything. So this brings us on to these power connectors here. So this symbol is how you can place connections of power for any sort of voltage, ground, 5 volts, your input voltage and so on. So if I click that and then I click over here to insert a power connector, we can type in ground, and up comes ground. And this is going to be your sort of shared ground across all your devices, and insert it here. And anywhere else now where I insert this ground symbol, it's going to be like I've connected a wire between those 2 points. So next, I should probably show you wires, obviously. So here on the right, you have the wire tool, also done by pressing W on the keyboard. So you can press W again, and now you can see these points are connected with a wire. So now both of those are connected to ground. Now we're going to insert another power connector up here for V in. So we're going to want to power the Arduino Nano with some sort of external power source. The Arduino Nano has this V in pin that will power it, and it has a voltage regulator in it. So you can power it off anywhere, I think, from like 5 to 12 volts, and it will regulate that voltage down to 5 volts for use by the Arduino Nano. So as we don't know what that voltage is going to be necessarily, we're just going to call it VCC, which is sort of the standard naming convention for your positive supply voltage. So again, we click that there, and now anywhere we're going to have a VCC connection, it's going to connect up to there. And yeah, so now we need to actually say, how's this connection to these two VN and ground connections going to get into the board from outside the board, basically. So we're going to want some sort of connector. So if you go to the add component again, you can see if we type in connector or just con, You get all of these different just sort of generic connector symbols that you can use. So for this example, we're going to want a 1x2 connector. I'm going to choose male for a moment. It doesn't really matter. We want 1 pin for ground and 1 pin for VCC. So you click OK and you insert that in the schematic. Another key command here, R to rotate, is very useful. I'm going to rotate it like that and place it about up here. And then again, we're going to add these power connectors, ground and VCC. R to rotate again, like that. You can see we have these names overlapping. It's quite nice to make sure that everything in the schematic is readable. You can use the M key to move things around. Press M, and then you'll pick up the label, and then click to put it back down. Again, move that over there, just so everything's a bit more readable. So now, in the eventual PCB layout, this will be how we're going to connect power to our board, essentially. Next out, I said the Arduino Nano has that voltage regulator in it that's going to regulate the voltage down to the 5 volts and the 3.3 volts that are needed for the Arduino Nano. We also want to sort of break that out so we can use that on other devices. So again, we're going to add another power connector here, because this is the 5 volt out here. We're going to choose 5 volts plus 5 volts. There you go, put that there. And on this one, we're going to choose 3 volts, 3V3. The convention, for some reason, in KeyCAD, when you're doing sort of voltages with a decimal point in, is to replace the decimal point with a V. I'm sure you've all figured that out by now. Yeah, so then we can again move this label up and out of the way. Sometimes if it's ambiguous what you're trying to move, or do any other operation to for that matter, it will ask you to clarify the selection. Normally it's a bit more useful than saying field value twice, but you just got to sort of guess and hope you get the right one. Normally it's not a bit less of a guessing game because it'll tell you what they are. Yeah, so that is all of the sort of power supply stuff started off. So next up, I think I will connect the potentiometers. So for those of you who don't quite know what a potentiometer is, I'm just going to say this anyway, just in case. It's basically so I'll get a picture up of one. Potentiometer. Yes, there you go. That's a sort of good image of one. So this is a potentiometer. It's basically a little knob you can turn back and forth, and it sort of has 2 resistors in it that vary depending on how much you turn the knob. So if you connect, say, 5 volts to this pin and 0 volts to this pin, it will act as like a variable voltage divider. And say you turn this all the way clockwise, you'll get 5 volts out on this middle pin. And then as you turn it all the way anti-clockwise, say, it will go from 5 volts to 0 volts. So you can use it to sort of input an analog value to the Arduino. So as we're inputting an analog value, we're going to need to connect these to the analog pins on the Arduino. Some pins on the Arduino can read in analog values, others can't. And this is sort of defined by, see these say D before them, these are all digital pins. These are all analog pins, A for analog. So here we're going to use another type of labeling. Before we had these sort of power labels. Now we're going to do a net or global label. So if we click this, again, it's going to be the same sort of thing as those power labels, but now we can just name them whatever we want. And this is more used for like connecting signals and things like that. So we're going to call this pot 1 for potentiometer 1. Again, rotate and put it there. And then pot 2 for potentiometer 2. So, we could connect these up with wires directly to the other stuff we're going to put on, but it makes it a bit cleaner if you do these labels, because then we can place the potentiometers wherever we want on the schematic. So our connection to the potentiometers, as you saw, it had 3 pins. So we're going to need 3 connectors. We're going to sort of connect it off the board, basically. You could have a connector to solder it directly onto the board, but instead we're going to use those pin headers I showed you before. And yeah, so for that, again, we're just going to insert a component. We're going to search connector. and we're going to go for a 1x3. So if we rotate that, just to get a line like that, and we'll sort of put it in the sort of general location where it would be, like near to the pin on the Arduino. But as we've done this nice labeling, we don't have to physically wire it up. We can just add the labels. And then I'm going to duplicate that by pressing the C button, C for copy, and put that down there. Next, we need to connect up 3 volts and ground, like I said. So it will vary between 3 volts and ground, which is what these analog pins can read. So we're going to connect up 3 volts here and here. And then we're going to connect up ground. Sorry, I probably should have mentioned earlier on, ground is just sort of the naming convention for the sort of negative terminal, basically. The sort of 0 volts line. I'm sure you all know that anyway. But, connect up the grounds, and then we can create these labels. We could just draw some wires between these, and that would work exactly the same way, but we'll use labels to keep it nice and clean. So pot 1. Now we place that there. These two are connected together. And we place pot 2 over here. And those two are connected together. Okay, so that's all we need to do for the potentiometers. And next, we'll just do some LEDs. So the LEDs will connect to these digital pins over here. Almost all of them can output PWM, so you could dim these LEDs and so on. I think we went over PWM in one of the lectures in first term, so hopefully you'll know what that is. So for inputting those, so we'll first create 2 LEDs. So again, you could just type in LED. This is one of the great things about KeyCAD, and you get up a symbol for it straight away. Rotate that, like so. C to copy. Place that one in as well. And then we'll click to put in another component. We'll just type in R for resistor. You can see we get sort of, there's kind of 2 types of component symbols in KeyCAD. There's sort of generic symbols, and there's like very specific symbols. For things like capacitors and resistors and like those very simple components, it's generally better to use sort of the generic symbols. So here, you know, we need an we need a resistor for limiting the current through the LEDs, and we need one on both. We'll do that. Well, that's in the wrong place, and to move. And then we're going to connect the positive side of the LEDs to the pins so we can turn them on and off. And then the negative side down to ground. So we're going to use that power connector tool again. And we're going to place a ground symbol there. And now we're just going to wire that all up. So again, W for the wire tool, W, 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 and so on. So we're going to connect these up to D3 and D2. This is all sort of arbitrary choices, really. You know what? Doing this demo PCB, it doesn't matter too much, but you'd want to check if you search like Arduino Nano pinout, for example. You can get this pinout, and it tells you what all the different pins have, like if they have PWM, if they're an analog pin, and so on. There's something to keep in mind. But yeah, those are connected up now, so you'd be able to control those, turn them on and off via D3 and D2. We can get some analog readings in from these potentiometers. And yeah, the final thing to do is, so it's quite an important concept in sort of general electronics design. It's called power supply decoupling. It's a bit complicated, but essentially you want to add capacitors across anywhere where you have a power line coming in, where you're not sure if the voltage is going to be very stable. So for example, if you have a set of AA batteries, and you have a microcontroller and a set of motors connected to it, you're going to want to do this power supply decoupling, because when the motors sort of turn on, they're going to draw a lot of current, and that's going to pull the voltage of the batteries down a bit because they're under load. And you don't want those voltage dips affecting your microcontroller. because if they do, it will essentially just reset the microcontroller and you're going to lose where you were in the program. So to do that, we just add capacitors across sort of the positive and negative power supply. And, you know, capacitors you can think of as sort of basically like a battery, not quite the same because they're, you know, they're very, very small capacity, but they have very quick response, unlike a battery. But yeah, they'll sort of fill in the dips in the power supply. So we will create VCC here and ground, because we're going to want to connect some capacitors across that. And then we're going to insert a component, and we're going to press C for capacitor. See, this is unpolarized capacitor. Yeah, so what that means in a second. I'm going to connect that in there. Insert another component, and we're going to type CP for polarized capacitor. So there's quite a few different types of capacitors, but more generically, there's two different types of capacitors. There's polarized and non-polarized capacitors. And it essentially means for polarized capacitors, it matters which way you place them around. You can imagine if you have two holes and two pins in your capacitor, there's two different ways you can place it. For polarized ones, there's going to be this little plus symbol on the component itself, and that has to be on the positive side or it will genuinely just explode. So yeah, and then there's unpolarized ones as well, which doesn't really matter which way you put them around. More generally, like polarized capacitors are just what's called electrolytic capacitors, and these often have a very high capacity, much higher than the unpolarized capacitors. So that's why we would use one of both, basically. So we have a small capacitor here that will deal with, it has a smaller capacity but a faster response time. So that will deal with very small sudden peaks. And this will be a much larger capacitor in terms of capacity and size, and will deal with sort of longer term, deeper spikes, basically, because it has a higher capacity. Yeah, so for the schematic layout, that is now it, I believe. That was all I was going to put on for this demo. So we will go to the next step, which is sort of starting to think about how we're going to turn this into a PCB. So up here in KeyCAD, there's a symbol that says assign PCB footprints to schematic symbols. So we have all these sort of generic symbols, but we have no idea what these are physically going to look like when we put them on the board. So now we need to assign some physical footprints that show how they're going to look like. So the first thing that's going to come up is it's going to say annotate schematic. So you can see, oh, sorry, I want to wait for that to be something. No, okay. Yeah, so you can see, for example, this connector here has J question mark. Now you could give these specific labels, say you could change this label and say it's the power connector and this is the potentiometer 1 connector and so on. But if you just click annotate, it will just call them J1, J2, J3 and so on. And it won't let you do the footprints until you've labeled those correctly. So now it's loading up the footprint library. So again, much like we had a schematic library whenever we were adding components with loads of different component symbols in, we now have a footprint library with loads of different footprints in. So we'll just wait for that to load. Yeah, there we go. So for some symbols on your schematic, you'll actually get the sort of this right hand side here tells you what footprint is being used, and this left hand side shows you what component it's for. So some of them, like this Arduino Nano, for example, have already been filled in for you, and that's because you chose a very specific component, so it knows what to do for it. Whereas these generic components, capacitors, you could have all different sizes of capacitors, different sort of configurations and so on. So it lets you manually choose what footprint to use. So if you want to view what footprint is currently being used for that component, you can click this up here. And you can see we get that layout that looks exactly like an Arduino Nano. I'll zoom in a bit for history. Yeah, like that. So you can see that's what it's going to physically look like when we put this on the board. Yeah, so now we need to go through each one of the components and apply a footprint for that. So you can see when I click on this capacitor, nothing's come up here on the right hand side because it doesn't have a footprint yet. So we can scroll through the different libraries on the left here, and we can see capacitors here. So this is going to be what we want. And this SMD and THT, SMD stands for surface mount device, and THT stands for through hole. We're going to be making this board all through hole because it's a lot simpler. So we click on capacitor through hole. And here you're going to get on the right a whole bunch of different footprints that you can use. And, oh, sorry. Yeah, with different dimensions and different types. So you can see these axial capacitors. They're little circular cylinders that are laid down on their side. And then if we scroll down, we get to ones that are called radial capacitors. They're now instead put upright, so you get sort of the top view of the cylinder now. So most often for the polarized capacitors, see CP here, polarized. These are going to be upright capacitors, and yeah, so the dimensions you choose will basically be defined by what you can find online for the capacitor you need. So, for example, if you can find one with a diameter of 5 mil and a pitch, P for pitch, that's the distance between these two holes. Yeah, if you can find one online with these dimensions, that's what you're going to use. So I'm just going to choose that for CB. And then for C, these are usually in a bit of a different form factor. I think it's usually called, yeah, here you go, like disk capacitors. Again, you know, I'm not doing any specific components here, so I'm just going to choose an arbitrary one, say that one. And yeah, same thing for all the other components. So LEDs, we scroll down here on the left, see if there's an LED section. Again, there's LED surface mount, LED through hole, we're doing through hole. And yeah, then you can sort of click through these and see what you want. I'm not sure if all of you have seen sort of a LED before, but they have sort of a circular thing with a flat side. And yeah, so this would be mounting the LED upright, pointing out the PCB. And that's kind of what we want for this. So we'll click that. And again, LED on that. So we'll click that. That applies them. And here we're getting onto the connectors. So I said we wanted to use pin headers like we showed in the presentation before. And here, if we look at connectors, we can see all sorts of different connectors. But the ones we are interested in is connector pin header. The standard that we talked about before is 2.54. So if in doubt, go over the standard. And then if you click on these, you get a few different types. This is if you wanted to mount it sort of horizontally. If you had some bent pins that wanted to go sideways out the board, you'd use that one. But we want these sitting vertically out the board. So we're going to choose those. Also up here, this might not be selected already if you're opening a new version of KeyCAD, basically. There's a few different filters. So if you click on these, so like, for example, this one filters the footprint list on the right here by the library that you click on the left, which is a very sensible thing to do. And it's usually already selected by default. One that's not usually selected by default, but is also very useful, is filter the footprint list by pin count. So you can see all of these pins that are showing up on the right here are like 1 by 2 or 2 by 1 because we have 2 connectors. But if I unselect this, you can get a massive list with like 1 by 15 and 1 by 9 and so on. So it's usually pretty sensible to click that as well. And then here on the right, you can filter by like the name of the component. If you knew you wanted specifically, I don't know, horizontal or vertical, you could type that in there and click that. And yeah, so we're going to just quickly click through those. So I said I wanted a vertical 1 by 2. This is 1 by 3 now. So I want vertical 1 by 3 and vertical 1 by 3. Finally, for resistors, I'm going to go through this quickly again. Resistor, through hole, and then we're just going to choose something that looks sensible for this. Something like that. Select those, both of those. Now we click apply, save schematic and continue. Press OK. So now we've defined all of our footprints, what all these components are going to look like. And now we can click this PCB symbol up here, and that's going to run the PCB Layout program. So we click on that, wait for it to load. And yeah, here we are in PCB which is the layout PCB layout program within KeyCAD. So the first thing we're going to want to do is click this symbol up here, which is update PCB from schematic. So this is going to bring in all of the PCB symbols and all of the connections we defined from the previous schematic. So you press update PCB, you can see all those symbols we defined come up over here. Close this, and now it's going to ask you to like put it somewhere in this diagram. Just going to whack it in the middle. And yeah, so now you just get to laying out your components. These little white lines in between components show you where these pads want to be connected to, basically. So usually you want to try and move components near to where they want to be connected to, for obvious reasons. So for example, move that over there. We'll use R to rotate it into sort of a sensible orientation, something like that. Put that there. Move this over because it wants to be connected over here also. Put it something like that. And you can see in this case, it's looking quite similar to how we had our schematic laid out. And that was kind of intentional, but it's not always going to be the case, especially if you have a very complicated PCB. So we're going to lay that there. That LED over there by the side of it also. And you can see for the moment, I'm kind of ignoring these ground pins. You can see these aren't anywhere near where they're meant to be, but that's for a reason. I'm going to show you that in a minute. Now we have these 3-pin connectors that were for the potentiometers. So these need to get, you can see the white lines here showing that they need to be connected down here somewhere. So I'm going to lay that out like that, I reckon. Something along the lines of that. And for example, when you have two connectors like this, which are serving very similar purposes, it's nice to group them together and make sure they're in the same order. I could have rotated this twice and it would have been 3 volts pot to ground, but then that wouldn't have lined up nicely with this. If you line them up nicely like this, it will make your wiring that you're going to do in a minute a lot easier. Finally, we've got this stuff for the power supply. So this here is our power supply connector. Again, I quite like to sort of, if you have lots of pin headers that are going to be on the board, line them up nicely, and that just makes the eventual PCB look quite nice and more organized, basically. So then we're going to line up this as well. And finally line up this. And yeah, these are all the power supply decoupling capacitors that I was talking about. And generally, you want to get these as close to the power supply as possible, because then they have the greatest, you know, they have less of a long resistance path to deal with, on the power of the board, basically. So now we're sort of quite happy with how this looks, I think. You know, it's reasonably compact and so on. I'm going to move these just to the right a bit, just to get them a bit closer, so our eventual board can be a bit smaller. And same with the stuff on this side. Again, using the M key. Yeah, so now that's reasonably compact. We're making quite good use of space, I'd say. And yeah, now we can move on to actually doing the wiring. And you can already sort of see how this is going to come together. You know, ignoring these lines for the ground ones, which we'll talk about in a second. Everything has quite a short path to go. You want to minimize the length of your paths, basically. And yeah. So in those, the first thing to do, I guess, is talk about how I'm going to deal with these ground lines. So one of the things you can do in a PCB is what's called a filled zone. So if I click this filled zone button, and then I'm going to choose what to fill this zone with. And this is going to basically put, wherever I don't have a track, it's going to put a connection to ground across the whole PCB, and you'll see what that sort of looks like when I do this. So we're going to select ground, and we want this on the front copper. So there's 2 layers of copper, as I talked about before, one on top and one on the bottom, or one on the front and one on the bottom, depending on what you call it. And yeah, so I want this to be on the front. Click ground, click OK. And now I can draw a box, and everywhere within this box is going to be filled with a connection to ground. So let's draw a nice square box. Double click to finish. And now there's a button on the keyboard over here, sorry, that there's a few different ways to show this filled zone. So now you can see, before I had these white lines between this ground and this ground, this ground and this ground and so on, but those white lines are no longer there because these are connected using this big block of ground plane, it's called. So that sort of deals with all the ground connections. And yeah, so now all that's left is to wire up the rest of these white lines. Earlier on in the presentation, we talked about the manufacturer's restrictions, and when building these traces, we need to think about that. So you can see here that they prefer tracks and gaps not less than 0.4 millimeters. So we need to make sure KeyCAD is making tracks that are no less than 0.4 millimeters. So up here in the top left is where the track size is defined. So we can edit some predefined sizes here. I'm going to add a new track size, and I'm going to put it to, say, 0.4 millimeters. That's sort of minimum recommended. For this sort of design, where there's not anything hugely power intense, you don't have to worry too much. You can basically use the smallest track size. But obviously, the more current you're going to have going through a trace, the bigger the track size you want to have. And that can be calculated using some online calculators if you just Google it. I did not do that correctly. So once you've added your size, you can change what size you want now. So I'm going to set it to 0.4. And over here is the wires, draw wires button. And now you can basically just click between two things and it connects them. And you can see at the moment, it kind of looks like it's merging with that ground plane. This is a bit of a quirk of KeyCAD. You have to press the B symbol on your keyboard, and it will sort of redraw that ground plane. And now you can see actually these aren't connected to that. Another way you can sort of deal with that, if this gets a bit annoying, you can see we can't really see any components behind this big red block. On the left here, there's a few different ways you can draw these zones. And this isn't changing anything about your PCB, this is just changing how it's displayed. So I'm going to leave it like that whilst we draw the wires. So W for wire. Oh no, not W for wire, that's in the schematic. Just click between the two, like this. 3.3 volts. You can see it needs to be connected up to there. Potentiometer 1 needs to be connected to there, and it will sort of automatically wrap around things. You can also, like, I could force it to go here by clicking there, and then clicking there and clicking there, so it doesn't go quite so near to that. That's sort of up to you. Click there to connect that and that. Finally, we're going to click between here and here to connect those. Click between here and here to connect those. Again, I'd like that. It kind of looks nicer. Like, rather than doing this, it looks nicer to sort of continue that track over to here and then bring it down. Just personal preference, really. And then connect that up to there. Again, I want to do the same thing, so continue the track. And generally in PCBs, you want to avoid sort of right angles. So don't draw a track that looks like that, basically. Stick with these nice sort of 45-degree angles. And yeah, that's sort of this PCB almost completed. We've defined all the electrical connections and so on. The last few things you might want to do is you might want to, for example, add some mounting holes, and KeyCAD has stuff in that for that already. If we click this add footprint over here, you can manually add footprints as well as the automatic ones. And I believe it's just called, yeah, there you go, mounting hole. So, you know, an M2 mounting hole, for example, or an M3 or whatever. And you can just click on that, double click on that, and whack in some mounting holes. And though that looks like a connection, that's actually going to drill a hole through it. You can sort of view what your PCB is going to look like if you go to view 3D viewer. And this will show you what your PCB is going to look like in the end. You can see where I put that mounting hole. Sorry, I'll make this full screen. Where I put that mounting hole, there's a hole now. So that's useful. And you can see our capacitors, our pin headers, the little LEDs, and the resistors. Some devices don't have a 3D model bit onto KeyCAD. So for example, you don't see our Arduino Nano here just because it doesn't have a 3D model already built in. But that's quite useful for seeing what the end PCB is going to look like. One final thing along a similar line of mounting holes is you can also define how they're going to cut the edge and what the sort of shape of your final PCB is going to be. So if you click on the right here is all the different layers you have. You don't really need to worry too much about these. The main ones you need to worry about are FCU and BCU. So that's front copper and back copper. When you're drawing tracks, like I talked about before, sorry, I should mention this, you can actually swap between layers. So you can see this at the moment is a red track. If I press V, there's a little gray dot that's shown up there. If I double click, you see that gray dot? That's a via that we talked about earlier. And now that has swapped me between layers and I'm actually on the back copper. So now I can draw a trace over here and I can cross over these traces because these are happening on two different layers. And then if I want to go back up, I can press V again for via. And now I'm back on red, back on the front copper. So that's sort of how you use the two different layers. Yeah, so that's front copper, back copper. Don't need to worry about these too much. Silk screen. These are like little labels that show up in the PCBs. Like all this text here, that's in the silk screen. F mask and B mask. So I wonder if I can show. You can see here, like this track here is covered in green stuff, but then all of a sudden it's raw metal. The solder mask is the stuff that covers up these tracks, basically. So that's what these two layers are. And finally, the one we're just going to look at quickly now before we finish off is edge cuts. So this will define how they cut the shape of the edge of the PCB. So, you know, for something like this, it's probably going to be quite simple. You can draw just a square using these graphic lines, or you can, for example, draw a square with some rounded corners. So like I can draw a line here, finish that off, and then I could draw like a rounded corner, say. And I could do that all round, but I won't do that now for the sake of time. But that would round off the corners of your PCB when it's eventually made. Finally, for production, now that we've got our fully designed PCB, what you'd need to do to get the correct files on the website, at least on the EDG website, there is the list of what files you need to send for them to be able to produce it. So you need to send those top and bottom copper layers that I talked about, top and bottom solder mask layers, and the drill file. And now this drill file defines all of these holes that are going to be drilled through the PCB, so you can do your through hole components. Thankfully, there's all these files are done for you basically in this one simple menu. If you go to File, Plot, you can see front copper, back copper. You can untick the rest of these that you're not going to need, front solder mask, back solder mask, and edge cuts. So you can keep those and you just click Plot. If this comes up, it just means you haven't pressed that B button to refill it. So you just click Refill. And now you can see where all of these have been saved. Finally, to generate the drill file, you click Generate Drill Files, you click Generate Drill File, and again, those drill files have been created. Now, for sending it to the EDG, you just go to this location here on your computer, zip up all these files it's generated, and email it to the EDG at the address on this website right here, EDG PCB. Yeah, I think that's about it from me, unless anyone has any questions.
Cool. Thanks. Thanks, Richard. I'll pause